So today we will discuss about the solution procedure for solving equation of motion. We already know the standard equation of motion for a multi-degree freedom system model is given by this. So if you are talking about a multi-degree, then I should say these are my matrices and my vector. Each one of them we know how to evaluate for a given system. For example, the mass matrix, the stiffness matrix, and based upon the Rayleigh model we can also work out the C matrix with the damping matrix, and then of course I can work out the f of t for different kinds of forces. For example, in the last lecture we discussed about forces arising from impact and non-impact waves. In the previous lecture we talked about forces arising from seismic effect on tethers. We also talked about conventional forces which is coming from springing, ringing responses, aerodynamic loading from different spectra. So we know how to work out them. Now the question is in the entire equation of motion, you will notice and appreciate that x is actually the one which is requested or required to be evaluated, which is the displacement time history, because it is going to be dynamic analysis, this is going to be a time history. So I must get a time history in terms of time, I must get the variation of how the displacement varies as the time progresses. Once I have this, I can always do a transformation of this to a frequency domain and try to find out the frequency content of this. In the last presentations we saw the results on both the time domain and frequency domain. One can easily convert them the either way to find out the content of this, because frequency response will give you the energy content of specific frequency, whereas time domain response will give you the amplitude in terms of the maximum value. So one can request and one can have both for better understanding. So in such equations of motion, it becomes very interesting that I must solve for the displacement vector as a time history. So there are many schemes available in the literature. The most common scheme and popular is the direct integration scheme. Which is one of the most popular methods used for solving equation of motion in a time domain. Now the word direct actually stands for, or direct refers to, the equation of motion is directly solved using numeric algorithm or numeric integration procedure or integration scheme without transforming the equation of motion into another form before the numeric integration is attempted. That is why it is called direct. So we do not do any transformation of the coordinates for this, so directly we get the answer. So numeric integration is actually a step by step integration procedure. The moment I say step by step integration procedure, there are two catchwords here. What should be my step size? Because the step size should be in such a manner, it should represent a continuous solution more or less. Okay, that is number one. Number two, the step size chosen by you should have some relationship with that of the overall T of the structure, that is capital T. There should be some relationship between the step size and T. Okay. Thirdly, the step size chosen and the integration scheme should give you unconditional stable convergence, otherwise there is no point in having any numeric scheme. So we must ensure that. Now there are some assumptions made in this case. What we try to do generally is, we try to solve the equation of motion as applied at any time instant. Equation of motion is generally solved, or preferably we would love to solve this equation of motion at any time instant. That is what actually I want. I want the solution of u of t or x of t at any time instant. But when you adopt or apply a numerical integration scheme, you will solve this equation of motion only at discrete points along the time scale. Okay. The moment I make this statement, you will have a question in the mind that when my solution is valid, what is meant by solution? I get x of t. By applying some scheme, I find x of t, which is a vector in this case, because there are 6 degrees of freedom, I get a vector. Okay. Maybe at t equal to 0.1 second, I get a vector. Similarly, the next vector can be at t equal to 0.12 second, the step size is 0.02 seconds. Let us say we fix the step size. We can fix it as close as 0.001 also to make it more or less continuous, that is all in our hands. Okay. But however, the solution what you obtain using this scheme will be discrete, it is anyway cannot be continuous. Okay. Now, the problem comes here is when you have got the solution applied or the validity of the solution as at every discrete points. What does it mean? When I substitute x of t at 0.1, it should feed back and it should give me the equation of motion valid at that particular point. What does it mean is the x dot and x double dot multiplied pre-multiplied with this should give me f of t at 0.01 seconds, that is the meaning actually. Okay. So, though f of t is continuous, okay, f of t is not discrete, f of t is continuous, because f of t, you know, it is actually a continuous action applied from the waves or any action coming on the structure, but you are picking up a discrete value and try to compare and say the validity of this solution. Okay. So, there is a very serious problem here. The problem is that when you know solution at x of t 0.1, x of t is 0.12, you are always assuming the behavior between this band of your choice. You may say it is linear, you may say it is non-linear, it is cubical, it is hyperboloid, you are assuming that. The solution does not give any nature qualitatively about this variation within the time step, that is very very important. So, you cannot interpolate between the time step. If you have a value at 0.1, yes, it is available. If you have a value at 0.12, it is available. Somebody asks you what is the value at 0.112, you cannot interpolate. Then in that case you got to rerun the whole scheme again, taking step size as multiple of 0.112 and get the value, but you cannot interpolate because the distance between or the interpolation nature between the time steps is arbitrary. Okay, that is one of the important catch here. Okay, it is seen sometimes as a demerit, sometimes does not in people mind, because people say I am making my step size so close, how does it matter? Okay. If you make it so large, then it really matters, but if you make it so close, it does not matter. But what is that step size which will make an unconditional stable solution? We must know that, and of course this step size should be having some fraction of the overall t of the system, the time period of the system. This t can be either the excitation wave period or it can be either the structural period also. So, you have to choose that. Okay. So, let us see what are those conditions available in the literature. Newmark has given a very interesting algorithm which is named after him, called Newmark's integration scheme, which we will see now in this class and show you the coding also for this. So, Newmark NM. That is the reference. Okay. This is named after him as Newmark's method, is actually Nathan Newmark's method. Okay. That is the method what proposed by him in early 80s, early 60s. Okay. This gentleman said or given an algorithm saying, if your delta t, the most vital part of this scheme, if the step size delta t, if the step size delta t is lying in the range of delta T critical or less than equal to this, then it gives you a stable unconditionally converging solution. Now, delta TCR is actually Tn by pi, where n stands for the natural period. Now, if there is a 6 degrees of freedom or multi degrees of freedom, Tn is the lowest. The least of all, and of course, n is the order. Or degrees of freedom, whatever it is. So, he has given a scheme. The scheme is like this. Let me write down the scheme here. Step number 1, form K, M and C matrix, and of course, f of t also, which is known to us, okay, for a given system. Initialize x0 and x dot of 0 and find x double dot of 0. It is very easy to know how it can be done. Let us say my equation of motion is mx double dot plus kx is 0 or f of t. If let I am not allowing damping to occur in the system, let us say for x 0 this becomes 0. So, I can easily find x double dot 0 as simply mass matrix inverse of post multiplier of f of t. I can get x this vector easily, okay. There is no problems, I can always compute this, okay. Once I get this, I must choose or select the step size delta t. We already have a governing given by the scheme manager saying that delta t should be within delta t critical. So, I know the time period because I do a natural vibration free vibration response. I will get the periods of all the degrees of freedom, pick up the lowest one and check that, and I can always check up, and I must also select and choose alpha, there is another variable or a parameter in the scheme, and delta. Delta is usually taken as greater than 0.5 and alpha is computed greater to be 0.25 of 0.5 plus delta the whole square. Let us call equation number 1. If delta is taken as 0.5 and alpha will become 0.25, as you see here, it is going to be 1 square 1 and 0.25, then the scheme is called Newmark's beta method. Okay. The scheme is renamed as Newmark's beta method. Then there are some constants required to operate the scheme. Let us see what are those constants. They call them as integration constants: A0, A1, A2, A3, A4, A5, A6, A7, 8 constants. Okay, 8 constants are there. 1 by alpha delta t square, delta by alpha delta t, one by alpha delta t, So, these are some integration constants recommended by the manager to operate this. Step number 5. So, till now for a given equation of motion you know this step number 1 is computed, then you can initialize these values, assume them, obviously you will assume them as 0 because that is how we generally do for free vibration analysis also, and one can compute x double dot naught, then one can fix up the scheme, find out these constants. Okay. Then form effective stiffness matrix. Which I call k hat. K hat is given by A0m plus A1c. For each time step calculate the following. Let us say 1 f t plus delta t, which will be given by f t plus delta t plus m times of A0 x of t, A2 x dot of t and A3 x double dot of t plus C of 1 A4 A5 xt x dot x double. Okay, I will put the plus here. Now, to compute a new revised force vector, you have to have these constants available to you, which is known to me. You should also have the values of response, displacement, velocity and acceleration at the previous time step, because this is t plus delta t, this is t. So, this I will know. The one which I will not know is this, because I want the force at the new time step of t plus delta t. So, to get this it is very easy, m x double dot t plus delta t plus c x dot t plus delta t plus k x t plus delta t is actually equal to f t plus delta t hypothetically. Okay, but I cannot get this value because I actually do not know x t plus delta t, x dot of this and x double dot, because I am actually calculating them. Okay. To start with, I will always say this value will be equal to the force at the previous time. Okay. So, that is the first one. So, x t plus delta t, which I wanted now in the new time step, will be given by f hat of t plus delta t by k hat, which I know from equation 5 or from step number 5. Then the third will be x double dot and x dot. There is a quick resemblance here, you can easily understand. If you look at the acceleration term which you want to find at t plus delta t, the coefficients recommended by the manager are same. For acceleration, which is mass associated, a0, a2, a3, a0, a2, a3. Okay, there is a catch here. So, you do not make a mistake there. And to compute the velocity at the new time step, you require acceleration at the new time step. So, you first compute acceleration, then get the velocity. Now, to compute the acceleration in new time step, you must know the displacement in new time step. So, you calculate the displacement first, then go to acceleration, then go to velocity, that is the scheme. Okay. So, by this way, in a given time starting from 0 to any value you want, maybe 10 seconds, 15 seconds, 100 seconds, whatever you want, divide them into equal number of delta t's. At every delta t, get a vector which is displacement, velocity and acceleration, which will give you more or less a continuous solution, but however the behavior between this displacement and this displacement at this interval is arbitrary. Okay, that is very important. So, you can make it as close as possible, it looks like continuous. Okay. This is a scheme suggested by Newmark. Now, let us implement this and understand how we can solve a simple problem. Then I will show you how this problem becomes more complicated when you attempt to solve this problem for compliant structures. So, let us take a problem simple, the example or exercise, whatever you call. Let us say I have a mass matrix, to make it very easy just for solution purpose, 2 0 0 1. I have a stiffness matrix 6 minus 2 minus 2 4. Do not bother about the units and do not bother about the significance of these numbers, just for understanding we are trying to adopt this scheme. F is 0 1 10. Okay. So, you have the steps with you, let us try to do this. So, the solution for this, I want to solve mx double dot plus kx is f of t, that is what is asked in the problem. So, I have to find x of t, okay, for different interval. So, step number 1, as you see from there, I have the mass matrix K in F. So, let x 0 be 0, x dot 0 be 0. So, x double dot can be mass inverse of f of 0, which is available here. Can you just find out this mass inverse of this? So, mass inverse is going to be 1 by 2 of 1 0 0 2 of 0 1 10 is going to be 0 10. Okay. Step number 2, I want to find fixed delta t. Okay. To find delta t, I must know the time periods of the given system. So, if you try to adopt any standard procedure what we discussed in earlier module, I am getting omega 1 square as 2 and phi 1 the first mode shape, 1 by root 3 of 1 and 1, omega 2 square is phi, and the second mode shape 0.5 of 2 by 3 and minus 2 by 3. So, let us work out T1 and T2 in this case, 2 pi by omega, which is 2 pi by root 2 in this case. Similarly, 2 pi by omega 1 omega 2, 2 pi by root 5. Can you give me these values? This 4.443 and this was 2.81 seconds. Is it okay? So, the lowest of this is T2. So, my delta T critical as advised by the manager is Tn by T minimum by pi, is it not, pi, which is 2.81 by pi, which comes to how much, 0.9 something, 0.89, okay, approximately. So, my delta T should be closer than this, lower than this. If it is there, it will give me an unconditionally stable converged value. Okay. So, for delta T lower than delta T critical, the solution will be conditionally stable. So, let delta T be removed. 0.28 seconds. So 1/10 of this actually, okay, 1/10 of this, and alpha be 0.25 and beta, sorry, delta is 0.5. So I am operating a standard Newmark's beta scheme. So I can also compute A0, A1, A2, etc. all till A8 or A7, sorry, I can compute them quickly. Please compute them. Step number 3, I want to find k hat, which is k plus A0m plus A1c. C in this particular problem is 0. So k already I know, which is 6 minus 2 minus 2 4 plus what is A0? 51.02 of 2001, which will be again a matrix of 2 by 2. Please compute and give me the matrix. Minus 2 minus 2 55.02. Now I want to find k hat inverse as required for finding out my displacement. So can you quickly get me the inverse of this? 2 by 2 matrix, it is 0.0093, 0.00034, 0.0182, and it is symmetric. Please check whether these answers are okay. Most of your calculators should have a capability of inverting a 2 by 2 matrix at least, so you should be able to do. Now I have come to a part where all fixed answers are placed. Now I want to go for each time step, calculation for each time step. So at t is equal to 0, I know x0, x dot 0, x double dot 0, I know this. Now I want to find at t equal to 0 plus 0.28, that is 0.28, I want to know this. So already you have the equations given to you in step number 3 or 4 given by the manager. So you can easily find out x t plus delta t, x double dot t plus delta t, and x dot t plus delta t, and keep on. Let us see the scheme here easily, which can be done in MATLAB. So I am going to, please see the screen now, go to the MATLAB. So the code is available there. For about, let us say, 55 seconds or 50-60 seconds close from 0 onwards, the degree of freedom 1 and 2 is marked on different legend colors: displacement, velocity, and acceleration. It looks like a continuous result. This is how you get the time variation of the displacement, velocity, and acceleration using a numeric integration scheme as suggested by Newmark in 1960s. Okay. Now at every point here, at every time step here, you get only one value of x, x dot and x double dot, but when you apply this scheme to a system where the complaint structures are involved, let us say, now let us see what is the complication we get when we apply this scheme. By applying this scheme to a complaint structure, say for example TLP. Why TLP? Because we have shown the results of TLP in the previous lectures. So let us see how, what is the difficulty here. The first difficulty comes here is very simple. In TLP, the mass matrix and K matrix and therefore the C matrix, because it is A0m and A1k, keeps on changing at every time step. Okay. And most importantly, K actually is response dependent. We already seen the equations for TLP, we know it is response dependent. and to some extent sum of the coordinates of M is also buoyancy dependent, what we call non-linearity arising from due to variable submergence. So therefore these two are not a fixed value as you had in this problem, they are changing. Okay. To start with, you will have M, K and C for the initial value of x only, okay, which is a static equilibrium condition. Okay. So initial value you will have, then you keep on updating. It means when your M, K and C is changing, the whole scheme of this will get iterated. Okay. It will not be unique. 2. Now you look at the equation for k hat. K hat is a function of k which is function of x. K hat in this algorithm is constant. It is out of the loop of the calculation every time step. Whereas in our case k hat will get into the loop because k hat becomes a function of displacement, but displacement is actually an unknown. Okay. So this is another issue, k hat. Now more serious issue is this: by any chance if your integration scheme is not proper in your analytical programming, inverse of k hat will fail. You will not be able to get the answer actually. It shows divided by 0, it will exit out of the program, it will not give you the answer, because there is a difficulty where you have done some mistake in your algorithm and k hat inverse does not exist. Okay, the scheme will stop, you will not be able to get the answer. And the fourth problem, very serious, is I want a convergence. Why I need a convergence? In this case if you see, at every time step starting from 0 or 0.28 or 0.56 etc., I have only one value, whereas in my scheme of TLP at 0.28 I initially have a k, which is based on x at 0, whereas my displacement at x at 0.28 should have a k at 0.28. So my k will get updated. The moment a k gets updated, delta t x at delta t will change. So I will get a new value. So this new value should have a k at that x of t, where I have a k only at this x of t. So keep on iterating. So I must iterate till there is a convergence of at every time step one x of t and another x of t is exactly converging. Okay. So this problem will be there in case of complaint systems. And additional problem, in all the scheme if you see the whole issue k hat or x of t, there is a divider at f hat t plus delta t, whereas f is also dependent on x, because I am having in Morrison equation x dot minus u double dot. I have a relative displacement. So if I do not have the acceleration at t plus delta t, I cannot find actually the Morrison force. Okay. This will also come into the loop again here. Now the question here is, if I do not know this in my algorithm, I cannot find u dot because it is f t plus hat by k hat. Both are now getting simulated or getting iterated. Okay. So to start with, at every point I will have nothing except the values of the previous point, but all the values at this point should be available at that point, which I do not have. So I believe that the previous value points are as same as the value points here, and find out the answer, see whether this answer is what I am assumed in the beginning and getting the same back again. If you do not get, keep on iterating in sense not only the displacement, you have got to start iterating from k, m, c, f of t. The whole equation of motion is getting completely iterated. Is it clear? And now the most important last confusion is, this convergence should happen at velocity, displacement and acceleration. Now there will always a scheme there, any one of them will converge, the other one will not converge. Okay. Therefore it is very difficult and complex that people do not apply this for complaint structures, and you will find very less analytical papers available on solving this by this procedure. Okay. So when your acceleration, velocity and displacement do not converge in the schemes, we focus on displacement. One can ask me a question, why displacement? Okay. compliant systems are displacement bound, they are not acceleration bound. The systems are actually meant for large displacements, that is why they are called compliant. Okay, so we compare with the displacements and check out. Okay. So, all these earlier solutions what you saw in my presentation for TLP solutions were based on analytical coding done on Newmark's beta scheme, which showed a very promising convergence, and we had seen the results very easily, where the schemes is given in most of the reference papers listed by me in NPTEL website. So, when you apply the scheme for a system which is compliant in nature, where the LHS and RHS of equation of motion are interconnected and response dependent, this scheme is not as simple as you see in the coding here or in the understanding in your mind, it is very complicated. Okay. So, however, when you apply this for a coding, you will get an answer of this order, where more or less the solution looks as if it is continuous. Okay. However, the behavior between the time steps are arbitrary. I can even plot them, I can even join them as a straight line, as a cubical line, any or spline curve, anything as per my choice. Okay. That is the catch here. So, I made it very clear that how the TLP solutions are obtained for equation of motion, what are the different kinds of forces which has been attempted. So, the next lecture we will focus on new generation offshore structures for ultra deep waters, where the design and development also goes with dynamic analysis parallelly. So, we will take up a new kind of a generation platform which is meant for ultra deep waters and see what would be actually the complication deriving the stiffness matrix for that system, and how the stiffness matrix or how the response behavior is seen when it is subjected to random and regular waves experimentally, analytically and numerically. Of course, in that solution we are not adopting Newmark's beta method, we are going for an inbuilt algorithm schemes available in the software like ANSYS Aqua. So, I will show you that, I will show you even the screenshots how to model them in Aqua, what are the difficulties arise when you model in Aqua. I will show them, I will also show the model, I will show an experimental video, I will show the solution experimentally, analytically and numerically, compare them, then I will show you how this was patented and how the project was, the problem is accepted internationally by many agencies. So, that would be the focus for the next 2 lectures to understand. Once we understand that we have done enough on FSI, we will stop there, move on to the last module where we will talk about stochastic dynamics. Okay.